So excited. We have a range of people here today. That's really good to hear. Sam, have you ever wanted to travel to any of these places?
Yes, I want to travel to every single one of them. When I
Every
finish my
single
master
one.
degree,
Have you,
maybe.
maybe. Would you be thinking of possibly doing a PhD over there?
Oh yeah, of course. Yeah, doing PhD elsewhere would be very nice. I do love Melbourne, and but also look into other places in the world for a PhD position. Yeah.
Yes, awesome. So that's really good to hear. I think like just having the wide variety of people here coming to join us today to listen to your talk is amazing. Did you want to
Hmm.
share your screen and get ready to get started?
Yes, of course. Let me share the presentation. Okay. So it's my introductory slides. Am I off to go, Ash?
Yes,
Right.
perfect. And we also have for the audience here today, do have some poll questions throughout this talk today. So we'll be able to chat a little bit about them and sort of what the thinking is behind them. But Sam, time to take it away.
So as what Ash has mentioned, there will be like a Q&A session on the back of this seminar. However, throughout the way, I do have some poll questions to engage the audience. I hope you enjoy my talk. And if you have any questions, feel free to ask them in the chat. I'm sure Ash will direct them to me in the end of the Q&A session. So let's begin our journey today. I hope I can cope with this at 4 a.m. But today we'll be talking about black hole evolution through cosmic time. And feel free to contact me through email and all that if you have any further questions you want to engage about. So before we actually dive into the details, I just want to give you a general overview of the scales we're talking about here. So on the left, we have an active galaxy. Um, so a galaxy is typically at a size of about 10,000 light years across. So that's the size of a galaxy. And when we zoom into the bright region of a galaxy that's being active, we call this region the active galactic nuclei, which is it can be abbreviated into AGN. When this active galactic nuclei is really luminous and it's really active, we call it a quasar. And a quasar at the center of a galaxy is only a size of about 10 years, about like light years. So quasars are among the brightest objects in the universe. They're powered by a supermassive black hole, as seen here as this M87 picture. Uh, and these black holes are accreting at a very high rate. This is why the quasars are so luminous. And as gas and dust spiral into the black hole, they form a hot, dense accretion disk shown here that emits intense radiation. So quasars, they often outshine the entire host galaxy. And that's part of the reason why we care about black holes. So given the fact that quasars outshine the galaxy, and we know that the hydrogen bombs, which is the most powerful weapon on Earth as at the current time. So how many hydrogen bombs do you think we need per second to get the same energy output as these like cosmic giants like quasars? So there are four options. Feel free to spam your answers in the chat and talk about like what you think. So the answers range all the way from one. Do you just need one hydrogen bombs to create like such intense radiation from black holes, or do you need like 1 million, 1 trillion, or all the way to 10 to above 23, which is a very specific number to get luminosity of quasars? And from the image, you see that it's really bright.
Yeah. So let's see people in the chat write their answers. I see that C is a very common answer at the moment.
We
We
have
have
a
an
lot
order
of
of
C's.
magnitude about 12. 12. Does anyone
Okay.
want to break that cycle? Anyone want to go with
Yeah.
the A, B, or D?
Why does no one choose A?
Everyone picks the middle option. Oh look,
Oh, someone picked
we
D.
got one person that is
This
breaking
very
the
specific
mode
number
there.
that I made up or not.
I wonder. We'll see. So we
Wonder.
got a lot of C's, a couple
So
D.
I see
I'm
throughout
so,
the audience, it's pretty at like we're choosing like a very high number, which is sort of what we expect, right? Like we need a lot of hydrogen bombs to create like the same intensity as these luminous objects like the sun, right? The sun is incomparable to the brightness of a galaxy, and even the sun requires tens billions of nuclear bombs to be at the same luminosity. So for a quasar, I guess I will show you the answer right now. A quasar is actually outputting its energy at 10 to the power 40 volts per second, and a hydrogen bomb is 10 to the power 17 volts. So it requires about 10 to the power 23, which is answer D. You need 10 to the power 23 hydrogen bombs per second to be as luminous as these cosmic giants. And just to give you, if you're unfamiliar with like what does 10 to the power 23 actually mean? So on Earth, there are about 10 to the power of 22 grains of sand. If you go to the beach and you pick up sand, it's a very small fraction of the 10 to the power of 22 grains on Earth. And then like with all the sands on Earth, 10 to the power of 22, you still need 10 hydrogen bombs per second for every grain of sand on Earth. So just imagine you go to the beach and you pick up like some pile of sand by your hand, and these sands, even if you give each of them 10 hydrogen bombs, they're still far less superior than the quasars, like these very luminous objects in the universe. So that gives you how like a view of how energetic these giants are. And we also care about the quasars because they co-evolve with the galaxies. So due to by current observation, every galaxy hosts a very massive black hole at its center. And if the black hole is actively accreting, these quasars, they represent a key phase in the galaxy evolution. So the rapid supermassive black hole growth is linked to intense star formation because there are feedbacks from quasars in the form of radiation, winds, and jets. So if you look at the image on the left-hand side, I don't know if you can see my cursor on the screen. Ash, can you confirm that? Yes, thank you. So you see there are jets coming from the center of this galaxy. And these jets are caused exactly by the accretion of the center black holes. And you see these jets, they extend on the same scale as the galaxy, and that's caused only by the center black hole. And as these jets propagate into the galaxy, you're going to create like turbulence, you're going to feeding metals. Well, in astro, we refer metals as anything that's heavier than helium. So you feed all the substances and you like cycle them in the whole galaxy. You create this whole mixture of the periodic table, which means you get like star formation in the host galaxy, and you regulate all the properties within the galaxy. You make the galaxy grow stronger and bigger. And on the right-hand side, we have the correlation between black hole mass and bulge mass. So this is also an observational thing. So it's observed that the mass of the central bulge, which is the proxy to, you can just view it as the galaxy. So a bulge is basically the host galaxy of the supermassive black holes. And we actually observe a linear trend between the mass of central bulge and black hole mass, which means that if your galaxy is larger, you get a larger black hole in the center and vice versa. So this just hints that quasars and galaxies influence each other's evolution over the whole cosmic time, which is why we want to study quasars, because we want to investigate in the whole universe, and the universe is dominated by galaxies. So let's dive into a bit more detail about what a black hole actually is. So a black hole is a region in space where gravity is so strong that nothing, not even light, can escape from it, as long as it falls into this short radius, also known as the event horizon. So the black holes form when a massive object, such as a large star, you need a minimum of 25 solar mass, so 25 times our sun. You need like this progenitor to collapse under its own gravity to make a black hole. And that collapse will give you a very small black hole, which we refer as the stellar mass black hole. So at the center of the black holes, there's this point we call singularity, where all the mass is concentrated and the laws of physics breaks down. If someone claims to you that they know what the physics are beyond, well, in the singularity, don't trust them. And surrounding the event horizon, this boundary, as what I just foreshadowed, beyond which, if you're forcing a matter here, a matter force in, nothing can return from the short rate, beyond the short radius. So black holes can vary in size. So they can be from a few times the mass of the sun, which we call stellar mass black holes. We define them to be ranging from 25, which is the minimum mass of a black hole, to about 100 solar masses. So, and there's also the intermediate mass black holes, abbreviated to IMBH. That's about 100 to 10 to the power 5 solar masses. And there are the supermassive black hole, which is the prime giants in the galaxies. They range from about 10 to the power 5 solar masses and all the way up. And you realize that on the left-hand side, I not only have the center black hole with its defined short radius, I also have the two orbits that we will dive into a bit more detail later. So first of all, there's the innermost stable circular orbit, short as ISCO. So this is the smallest orbit, as what the name suggests, around a black hole where a particle can stably orbit without spiraling inwards due to relativistic effects. So if a particle goes beyond this orbit, it will basically fall straight into the center black hole with minimal orbit spiraling. And we also have the self-gravitating radius. This is a point in an accretion disk where the disk's own gravity becomes comparable to the black hole's gravity, which means that beyond this radius, so outside of this radius, the disk can become gravitationally unstable. So you have fragmentations and possibly like star formations with the outer regions. So this means that the stuff outside of this radius is less likely to be swallowed into a black hole, or they feed to the center black hole at a very, very slow rate. So this is a brief overview of black holes. And black holes are actually really hard to observe. So you might have seen the picture of the M87, which is a donut-shaped picture taken by the Event Horizon telescopes. So as we know, the resolution of our telescopes is proportional to the size, which is the aperture of our telescopes. And the Event Horizon telescopes is an aperture synthesis of a lot of radio interferometers across the whole Earth. So, which means that if you treat all these radio interferometers as one whole telescope, its aperture is basically equivalent to the diameter of the Earth. And with this powerful resolution, so remember that your resolution is proportional to the diameter of your aperture. With this like extremely massive telescope size of the Earth, you can only resolve two black holes at the current stage, which is one is M87 and the other one is the black hole at the center of our Milky Way. So beyond this, I believe that beyond M87, the black holes become really hard to resolve because they're so far away and you cannot directly image them. So it's really hard to directly observe black holes. There are some other ways to observe black holes directly. For example, if you look at our own galaxies, our own galaxy center, and if you recall from Newton that the motion of stars would follow whatever the central black hole gives them. So there's this equation that governs the velocity of the stars that's moving in the center. And on the right-hand side, there's this GIF that all the stars are rotating with respect to this sort of invisible point. This invisible point in the center of this image. And from observing these orbits, we can calculate, well, first of all, you to average all the velocities of the stars and do some statistics over it. But you can use this to directly measure the mass of the black hole in our own Milky Way. And of course, you can only measure one black hole with this method because you cannot resolve individual stars in other galaxies. And I do see questions in the chat, but I think I'll address them in the end of the talk in the Q&A session. So this method called direct measurement, you can only do it once to our center black holes. Black hole. And the other option is to measure the black hole mass using Doppler shift, so Doppler effects. So if you imagine an ambulance coming towards you, you hear like a higher frequency, a higher pitch in the sound that the ambulance makes. So it goes. I'm not sure if I'm making the right sound, but the pitch to go higher when it comes closer to you, which means it's more blue shifted. And if it's going away from you, you receive a lower frequency, which means the light or the frequency is red shifted. So if you look at other galaxies, so you can only look at close by galaxies with this method. And if they have a supermassive black hole at the center, so remember supermassive black holes are the ones that reside in every single galaxy, they possibly have materials that's going around them, like this disk structure. So if you do a spectrum on this disk, you realize one side is going away from us and the other side is coming towards us, which means that this is rotating this way, and you can sort of imagining a head. And by measuring the velocity of materials going spiraling in this disk, we can do the same thing as before, measure their velocity, and hence indicate the center black hole mass. So about 100 supermassive black holes are measured with this method and similar method. So you can only apply this method on galaxies that's sufficiently close by, where you can actually do a spectrum, perform a spectrum fit on the materials that's going around them. But this is only performing measurements in the electromagnetic wave band. There are also other ways that's not using light to detect black holes. And this is, you might have heard about this. This is called the Laser Interferometer Gravitational Wave Observatory, LIGO. So when two black holes or a neutron star spiral inward and merge, so if you look at the right-hand side of this slide, they emit gravitational waves with increasing frequency. So as they spiral in towards each other, the spiraling becomes faster and faster. And this creates ripples in space-time. So you can imagine the space-time getting, if you throw a stone into a pond, and the pond will wave with ripples. And LIGO uses laser interferometry to measure tiny change in distance. It has two long arms. Each is about 4 kilometers wide, arranged in an L shape. So a laser beam is split and sent down to both arms, and they got reflected in the end by mirrors, and then they recombine at the center. So if a gravitational wave passes through the detector, it stretches one arm and compresses the other by a very small scale. So it's less than 1,000th the diameter of a proton. And this change shifts the laser interference pattern, and this will allow LIGO to detect the wave. So so far, there are about 100 merger events that's measured between stellar mass black holes, which is the range that LIGO operates in. So you see, this is a comprehensive merger events given by LIGO. Maybe this is a bit outdated because it's only towards the end of the O3, which is their third detection survey. This is end of 2020. They will have much more, I believe. I believe it's around 200 and plus. They have about 1,000 or 2,000 detected in the next few years, I believe. But you see, across all the merger events detected, you only get stellar mass black holes, which is ranging from 25 to 100, and some of them are, I think, is slightly above 100, but you only get black holes within this range that you can detect. So we talked about supermassive black holes, we talked about stellar mass black holes. What about intermediate mass black holes? And the short answer is that they're only candidates so far. So this is the Omega Centauri, and the current frontier research believes that there is an intermediate mass black hole resides in the center of this star clusters. So you really need to do this by studying like stellar kinematics within the center of these clusters, and they are really I can tell you they're really hard to do because you get trillions of stars in this cluster and need to map like individual or the kinematics of a bunch of stars in the center, and that's really hard to do. If you remember what we talked about, so we have about 100 black holes detected by LIGO. We have about 100 black hole masses detected using spectrums, and one detected by direct imaging, which is two detected by direct imaging. So why do you think black holes are so hard to observe directly? So there are 5 options here, and this is like a slightly trick question. So please feel free to express what you think in the slides, but I think I've gave enough hints. And this is a perfect time for me to sip some water.
So let's see in the chat what people have to say. Ooh, we have 5 options here. I love how one of the options is all of the above because it makes people think it makes people think that we should pick all of the above because all of the above is present. So we have behind dusty clouds, so the dusty Taurus, we have not accreting, too small, too massive, all of the above.
Yeah,
we have a lot of E's
why
here.
too massive? How can't you detect a black hole that's too massive, Ash?
Yeah, I wonder how big can a black hole grow?
Yeah.
There's a lot of things. Oh, I love how one person has decided to break the chain.
Oh, some people
This is
pick.
good.
So if you pick E, you have to realize that there's a small range of black holes that you can't detect, and there's also a very large chunk of black holes you can't detect. So think
Let's see as everyone goes in. But most people seem to be going with E.
Okay.
People are going with E. People are going strong. E is the lucky letter today, Sam.
Okay, that's good. Perfect. Okay, and time for the grand reveal, and the answer is indeed E. So you might be a bit shocked. Like black holes, if they're too small, you can't detect it. If they're too big, you also can't detect it. And let's dive in why. But first of all, let's figure out why the first 2 options are making you hard to detect black holes. So if we go through the detail of like the active galactic nuclei, so this is called the unified model of active galactic nuclei. This explains the different observed types of AGNs as the same underlying structure seen from different angles. So you have at the core of this AGN, you have a supermassive black hole. This is the little black dot at the center, and you have a surrounding accretion disk, which is emitting intense radiation. And then you have a dusty torus, that's we call a donut shape. So you can see it's composed of clumpy gas and dust. And then often in this unified model, you have a relativistic jet that's coming perpendicular to the torus and propagating outwards. So the difference between a lot of types of black holes can basically be explained using the concept of viewing angles. So if you are sitting on the right-hand side of the slide, right, you basically have a highly beamed energetic jet that's coming directly from the black hole, center black hole to your eyes. And you'll be sitting there and like, let me grab my sunglasses. It's like sitting down on like a very sunny summer beach, and you have to have like all the sunscreens and sunglasses in order to stay alive. Otherwise, you get sunburns. Please get sunscreens if you come into Australia. But if you view it sideways, right, your sight are basically blocked by this dusty torus, and we call these quasars, we call them obscured quasars. You can still detect some light because the dusty torus themselves are thermal, and thermal, as we know, black body, they emit radiation if they're hot enough, and quasars are hot objects. But you cannot, it's not as intense as like detecting jets. On sideways, when you see the whole accretion disk structure and also all the materials that's going between the dusty torus and the center black hole. So you see all that if you're on sideways, if you're seeing the jet face on, but you see nothing when you go sideways, you can only see the dusty torus. Just to remind you on the scale, so on the center is the little M87 that we all love. So this is only the center. And we have Homer eating the donuts on the right-hand side. Although I think they should make him eat the dusty torus, because that's the actual donuts that it's supposed to be eaten. So if we zoom into this accretion disk, here I'm going to refer to interstellar, which is actually a scientific representation of what a black hole accretion will look like, given general relativity. So for now, we're going to ignore the branches on the top and bottom because they're lights that's getting redirected by lensing effects. We're only going to focus on this side accretion disk. So an accretion disk basically generates light as matter spirals. So you can see they're spiraling into a massive object like a black hole. So friction and gravity, this we call it viscosity, it hits the gas in the disk to extremely high temperatures, like 10 to the power 7, 10 to the power 8 degrees. As particles in this disk collide and compress, they convert gravitational energy into thermal energy, which is heat. And this hot gas emits electromagnetic radiation, mostly in the optical, ultraviolet, and X-ray ranges, depending on how close it is to the black hole. So as you go inwards, the temperatures are higher, which means you get more towards the shorter frequency of a higher energy wavelength. And realize I have like little asterisks here. The luminosity from black holes are not only from heat, not only from thermal effects like a black body. It also comes from all these scattering effects between particles within this accretion disk and other things. But the catch is that you really need an accretion disk to see light from a black hole. So imagine if you don't have accretion disk, you only have a black hole in the center. You only see things like this. So the black hole, because it's so massive, it's gonna cause a lensing effect. It's gonna basically act as a lens, and it basically redirects light from the back towards you, but you're not gonna see the black hole shining so luminously. You're gonna miss that whole structure. And also, this is a problem because if black holes are too small, yes, they redirect light, but you don't know what's behind it, right? You only need you have to have some bright objects at the back, and it gets redirected, and oh, that bright source, I thought it's a galaxy, but it looks a bit weird. So you get an elongated shape if a galaxy is lensed, and you'd be like, oh, there must be a black hole that sits between the galaxy and the observer. So that's how you know there is a black hole sitting there. But if you don't have accretion disk, the chance of getting lensed is really low. So we prefer, well, scientists all prefer the black holes to have accretion disks so that we can detect them. So let's go into details about how big can a black hole grow. So previously we gave the range of supermassive black hole from 10 to the power 5 and all the above. But is this actually what we see? So if you go back to the original structure of black holes, we got the Schwarzschild radius, which is the event horizon that's defining the black hole region. We have the innermost stable circular orbit, which we'll refer as the ISCO from now on. We got the self-gravitating radius. And then the accretion disk, which we saw earlier, sits between the ISCO and the self-gravitating radius. Because inside the ISCO, stable circular orbits are no longer possible because matter that crosses the ISCO will rapidly spiral into the black hole. So it leaves little time to radiate energy away. As what we see previously, we need the accretion disk to generate heat and generate luminosity. So the inner edge of this accretion disk is set by the ISCO, which is dependent on the black hole mass. And we have the outer edge, which is called the self-gravitating radius. So as what we alluded earlier, there will be minimal mass accretion beyond this radius, which means that the accretion disk is going to stay between the ISCO and the self-gravitating radius. However, as your black hole grows and increase its mass, the innermost stable circular orbit would actually propagate outwards because you get a larger black hole. So you get a larger radius that matter comes in, it will fall basically straight into. So if the black hole grows, it basically becomes the picture on the right hand side. So you got this shrinking in accretion disk. So the accretion disk gets smaller and smaller because the ISCO increases with mass. And at about 10 to the power of 10.5 solar mass, when the black hole gets to that range, you basically have no accretion disk. And what this tells you is that if you don't have an accretion disk, you can't have light coming from this black hole. So you don't have a quasar structure, which means that you're not going to observationally see the black hole. Yes, the black hole is still there. It can do lensing and all the fancy tricks. However, you're not going to get a quasar structure. And that basically limits our observational. Remember, that's the observational upper limit on black hole mass. Beyond this limit, black hole can still accrete. Just they can't emit in electromagnetic waves. Matters can still swallow into because there's nothing stopping blacks from growing beyond this point in time, and this means that there are a lot of black holes. Remember, we have the obscured black hole, obscured quasars that's hidden from our view because they have dusty torus, and now we have black holes that's too big that we can't see. So there's a lot of population within black holes that's actually we're not actually able to see. So how do you grow a black hole? So a black hole basically changes its mass with two basic approaches. One is accretion, which we gave it like an illustration of accretion disk from an interstellar before, and then we have mergers. This is the thing that's detected by LIGO. So how fast can black holes accrete? So there is an absolute not absolute, which I'll go through it in a bit more detail. So there is an theorized Eddington limit on accretion, which is the upper cap on how a black hole can grow its size. So as matter falls in towards the black hole, it heats up because as it got closer, it heats up and there's more temperature, and this temperature will emit radiation. But this radiation serves as an outward pressure on the infalling gas, right? This is called the radiation pressure. And when the outward radiation force balances out with the inward gravitational pull, the accretion reaches the Eddington limit, which means this is this maximum steady accretion rate before radiation pressure blows away the inflowing gas. So imagine if you have too many things going in, too many things that's close to the center, you're going to have a very massive radiation pressure, and that pressure is going to cause a shock, which means you blow all the outside gas away, and that means you have no fuel to feed the black hole. So a small fraction of the matter in this accretion disk gets converted into light, and the leftovers are swallowed into black hole for its growth. So from this Eddington limit, we can construct a correlation between the maximum luminosity and the black hole mass. And following the Eddington limit, the EFO time, which is if you do a geometric series on how black hole grows, this is basically it grows the time it takes for a black hole to grow by a factor of E is about 45 million years. And keep this figure in mind, because we will need it right now because we encounter a crisis. So given the overall Eddington limit, JWST, which is the James Webb Space Telescope, it discovers an overabundant amount of supermassive black holes in the early universe. So just looking at this picture, it looks so you don't have to look at all the other details, but you get a lot of higher redshift, which means they're early in the universe. That's very high redshift galaxies. That's very massive. However, if you put a star that is about to form in basically 200 million years after the Big Bang, if you follow the Eddington accretion, it does not match up with these galaxies or quasars. So you get this about 2 orders of magnitude lower in mass that you can never achieve. So do we think that it's possible to accrete faster than the Eddington limits? Oh, and Ash just gave me a thing that we only have about 5 minutes left, so I think I'll speed run this. So I think I
Anyway, let people. Let's do this. People A, B. I'm interested to see what the results are. As someone that knows the answer to this, I would like to see what people think. Don't stress. There'll be time for Q&A and all that too. But so far we have B.
a lot of B.
Oh, a lot of B. A lot of B.
A lot of B. So we believe that the thing will just go blown away and no matter will get accreted. Nice.
I'm interested. Okay, we got 1A. 1A. I'm very, very hopeful for the person that has said yes.
A few Y, which I assume it's yes.
Yes. We've got a few.
Okay.
It's 50-50.
Okay, 50-50. I'll do a grant review now. So the answer is yes. So we so the model I described earlier is a perfect spherical accretion. However, for black holes, this is not always the case. For example, on the left-hand side, you just see the simulation. Black holes are spiraling inwards, and you definitely don't see like a laminar flow. It's mostly turbulent. And at extreme cases, the black hole can even have a lot of accretion disk. So this is called a warped disk structure. That basically creates chaotic accretion of black holes and makes it exceed the Eddington limit, because there's basically it's very hard to blow mass away at this point. So now it comes to the thing I actually do. So how do we simulate growth of black holes? And before I step into what I actually do, I'm gonna do a quick overview on how people usually do it. So usually it's conducted by large-scale M-body sims. So these are numerical tools that are designed to model the gravitational evolution of particles. So this is about, so just giving you a brief scale of this image. The units here is 31 megaparsec, but don't worry, this is about 10,000 Milky Ways within this distance, and you can see how massive this scale is. And you see this all beautiful simulation However, it does come with a caveat, which is why me and my supervisor are doing it in another form. So the caveats of these embodied sims include basically the simulation cannot model all black hole mass at the same time. So as we talked about earlier, we have stellar mass black hole that's from 25 solar masses, and all the way we have up to like 10 to the power of 9 solar mass black holes. So you can't simulate all black holes masses at the same time. If you want to simulate supermassive black holes, you have to feed in at least a very heavy intermediate mass black hole in order for the system to run, because the computer just doesn't take the dynamic range. Bear in mind that there's like a 5 order magnitude difference between the seed and the actual black hole. And then fine-tune the microphysics is complicated but very important, because you need to take into account of all the magnetic fields, all the turbulence, all the hydrodynamics, and they're very difficult. And also computation of these can take months, and they're very computational heavy. So can we make something that models black holes, models all black holes at once? The answer is yes. There is an analytical approach, which is called the continuity equation. So if you remember what we talked about earlier, we got change in mass equals to accretion and mergers. And accretion is relatively easy to model, because you just look at the light that's coming from all the galaxies, and you basically detect all the central engines, the black holes and the quasars, and then you sort of allude to whatever mass population you have within these galaxies. And these two images are screenshot from the Sky Viewer app. So this is the new Vera Rubin Observatories platform that you can basically zoom into all their galaxies. And with powerful equipments like the Vera Rubin, I hope all of you have seen the first sight of Vera Rubin a few days ago. We will get basically the whole sky in 10 years, which means we get trillions of galaxies that we can measure black hole lights from. And then integrating them will give us the population of black holes at different epochs in time. So accretion is relatively simple, because we have a relation between luminosity and mass. But what about mergers? So as we talked about earlier, LIGO can only detect stellar mass black holes. Just a reminder on what we talked about earlier. But then there's another thing called pulsar timing array, and pulsars are basically highly magnetized, and they are rotating very fast, but precisely you can sort of treat them as a lighthouse. And when two supermassive black holes collide, and it's the same as stellar ones, they also create ripples in space-time, and then these ripples will make will change your detection on the frequency of these pulsars. And remember, pulsars are very frequent timers in space. So you change the frequency of a population of a population of pulsars, and then using this, you can measure the background population of black holes that's causing all these ripples. So pulsar timing array basically detects supermassive black holes and binaries of them. So the continuity equation, which is like what I work on, basically work as follows. So you start with a test initial mass population, and you add more mass to the whole range due to accretion, and then you distribute the mass within mergers. So remember, we have the gravitational wave detector LIGO, and now we have the pulsar timing arrays that's dealing with both ends. And then we distribute the mass, and after that, we evolve the population to a current epoch, and we compare it, for example, to the LSST data, the Vera Rubin Observatory data, and see if we got the same thing. If we don't, we start with another test mass function, and we start this whole thing over again. And that's how we get to the end. And hopefully we'll come up with some mass functions. This project is still ongoing, so I don't have any result yet. But here is a general overview of the process I'm going to take. And this presentation comes to an end. Just in recap, sorry if I butchered too many things on the end, but so black holes are highly energetic and important to our galaxies, and a large population of black holes can be hidden as the population evolves. And also the continuity equation, which is what I work on, can serve as a quick and easy approach to model the average behavior of the population in a larger mass band. Which means that you can hopefully you can resolve the supermassive black holes and the stellar mass black holes at the population at the same time. And this is basically it. Sorry, I dragged the time a bit too much, but I think I'll let Ash take it from here.
Yeah, perfectly on time. All good. So thank you so much, Sam, for being able to present to us today. We do have a couple questions for you, so it might be handy to keep the slides up for people to go through. But we had our first question just before. I answered it a little bit roughly in the chat, but I think you can answer it a little bit better. It is, has there been any research on peculiar galaxies and any anomalies in the nature or size of their black hole?
Yes. So of course. Kevin, yes, Kevin. So we know that the galaxies, not all of them look like exactly like this shape, right? There can be interacting galaxies, there can be like dwarf galaxies, and so on and so forth. There will be galaxies that are very diffuse, for example. I don't know if you, okay, I'll call the Large Magellanic Cloud as a dwarf galaxy, but they're very diffuse and they do not exhibit the same shape or morphology as the ordinary galaxies. So the peculiar galaxies, for example, the dwarf galaxies that I just talked about, some people believe there are intermediate mass black holes that's hidden inside these galaxies. And on other peculiar galaxies, sometimes you get 2 or 3 supermassive black holes in the center, and they interact and they have all the feedback as we see here. There's like jets and all that, and that will add to the peculiarities. And people love to do research on them because they show how the black holes can regulate the peculiar galaxies and also the intermediate black holes in the dwarf galaxies. Yeah.
Good answer, Sam. And also, like, there's so much research going on with black holes too. It's such a wide field in physics. Like for me, like for the people that joined a little bit later, I work on quasar orientation, and that inside a quasar there's a supermassive black hole. So there's a lot of things you can do there. We do have another question. One of the questions we'll start with. This one is: does this mean that we will only have a picture of 2 black holes?
Okay, so this image, so this M87 and the black hole at the center of Milky Way are taken with this Event Horizon telescopes, so EHT. So as what I talked about earlier, you get this aperture synthesis, you accumulate all the telescope's data, and you create basically a proxy of a telescope that's the size of the Earth. But if you're adding more telescopes, of course, you're going to increase in the angular resolutions and all that. So if, for example, if you put another telescope here, you put another telescope there, you're going to increase the resolution by a bit, but not much. However, people are starting to propose to send these telescopes into space. So actually doing interferometries in space will, increase your aperture size to the solar system level. For example, we can put ones at the Lagrangian points, which is where the JWST is sitting right now, and that will increase the diameter here, which is distance from Earth to Lagrangian point. It will increase this diameter by a massive amount, and hopefully we can resolve the other black holes using this way. But bear in mind that this method is still limited to, I think, to black holes that's within the local group, because the other black holes are just like trillions of light years away. That's even with like a solar system scale telescopes, I don't think at the top of my head it's able to resolve them. But you can increase like the amount of pictures we have by at least, I don't know, couple hundred if we have a solar mass scale, solar size, what's it called, interferometry. Yeah.
Awesome. We also have one more question in the Q&A, and that is: do current models of the universe formation explain large black holes forming so soon?
So you really need to talk to the cosmologist about this. There are a lot of ideas that's being proposed. So there are two bands here that I just butchered through. I didn't mention them at all. So they are this first one is DCBH. It's referred to the direct collapse black hole. So instead of forming a star at the very early universe, you basically form a very large chunk of cloud, and then you directly collapse this massive cloud into a black hole, which means that you get a very large mass black hole at the earlier time. And then like with Eddington accretion and super Eddington accretion, which is the dotted line, you may get the high redshift active galactic nuclei observed by JWST right here. So that's one way to get it. And the other way is by population 3 stars. So population 3 stars are referred to stars that formed in the primordial stage, where they're only basically only hydrogen, and they are theorized to be very, very massive. So not as massive as the direct collapse group, but still massive enough that it can grow with an Eddington limit to most of the very massive very massive quasars that we see at the early universe. So there are these two, but none of them at the current stage. I don't think any of them has like a set result yet. They're all like candidates. I believe there are multiple candidates for population 3 stars, and people believe they can create like gigantic gamma ray flares and all that. And direct collapse black hole, people propose them. I think this paper is like 5 years ago. They proposed them to be a redshift of 15. Now they're proposing it to be a redshift of 20 or 25, which is about like 100 million years after the Big Bang. So they're pushing the time earlier and earlier. There are also other models such as the primordial black holes. So black holes that's formed when the universe is like basically when the universe starts. And these black holes can accrete faster, of course, because you don't need to form gas and clouds in order to form black holes. There are also like other methods that's preferred by cosmologists, but so far none of these methods has like a confirmed result yet. So we'll stay in tune. Maybe one of them is right, or maybe all of them is right. Maybe all of them are right.
Awesome. And this question I'll just answer from Kevin. Will this presentation be available? Yes, it will be. So this presentation is being recorded, so it'll be uploaded to the iTelescope YouTube channel and also to the Discord. Also, we have Sam's contact. So if anyone would like to contact Sam, he is very, very approachable. Just contact him by email and he's more than happy to answer any questions you have. I think today let's end it there. So thank you so much for coming to join us today. We really appreciate you coming here, being able to listen to Sam talk about black holes. Sam, your research sounds super interesting and it's going to go huge places, I know, in the future. So we're looking forward to seeing the results at the end. Please stay tuned for next month, where we have a speaker from Barcelona coming to talk about the cosmic microwave background. His name is Rao, and if you really enjoyed this talk today, you'll definitely enjoy the one in July. So with that being said, thank you so much and enjoy the rest of your day. Hopefully you haven't started your day today and you're at a much better time than we are. But we look forward to seeing you again soon.
Thanks, people.
Thanks, everyone.